Okay, so welcome back to System Software. Last time we went over some of the fundamentals of navigating the file system on the command line. We went over the file system itself. Hopefully everybody more or less understands the nature of a hierarchical file system. We read the original Unix paper that described their version of the hierarchical file system. We did some exercises learning about paths, how to refer to files on the file system. So relative versus absolute paths. What are absolute paths? They're always from the root, and the root, how do you denote the root in the Unix world? // So if the path starts with // you know it's an absolute path. Relative paths, what are they relative to? The working directory. So this is another Unix design decision. Every running program has a working directory that the kernel, the operating system, actually maintains. And this helps with that interactivity. The command prompt, as we saw when we navigate the command prompt, you can type what to learn what your current working directory is. pwd, print working directory. So every running process has a current working directory associated with it, and that's what relative paths are relative to. So this time, I'm going to give a little background on the theory of processes. We talked about the file abstraction before, which you also read about in the Unix paper. And we're going to talk about the process abstraction, another one of these fundamental operating system abstractions that the kernel provides to you. And we'll go over, we won't go into how it's implemented, but we'll go over enough for you to kind of get the idea, and then you'll read about it in the Unix, finishing up the rest of the Unix paper. They'll talk about their design of the process abstraction. And then I'll do some more command line illustration to show you how to work with processes on the command line using the kind of Unix philosophy. Okay, but first let's go over the homework from last time. So the homework from last time was to make sure you can get into Eustace. So is everyone able to, who can get into Eustace? Who cannot get into Eustace? Is anyone still waiting to access? Okay, good. So everyone can get into Eustace. You can all SSH in. Did anyone have issues with downloading files, untarring files? Any questions on that? So you'll be able to, or I don't think you need to download files, but you'll have to like clone or use other web resources. So I want to make sure that you can access it. Yeah.
What does it mean to untar a file?
Oh, so sorry. Tar is the Unix style archive tool, an archiving utility. So it's called tar. It might come from tape archive. I'm actually not sure. Oh yeah, it stands for tape archiver. So it's just the utility for making these archives, which are just like zip files, like sets of files compressed into one format, one file. It's called a tar, also called a tarball for some reason. Did I actually say that in here? And so to, like with unzip, to unpackage or unarchive these, the lingo is untar, or at least that's what I'm using. Yeah, they don't actually use that term, but yeah, when I say untar, I just mean unzip or unpackage the tarball, and a tarball is a file archive like a zip file in the Unix world. This is the kind of Unix world version of zip, actually predates zip, and it's not compressed by default. Okay, so who felt like they got the whole homework? They actually got it done. Pretty good. Anybody have questions or is struggling on some of the, or wants to admit it, that they having issues with it? All right, so let's go over it. Let's go over it quickly anyway, for those who might have questions. Yeah.
What does that -xbf part mean?
Oh, so yeah, I put a quick documentation of this in the slides. X means extract as opposed to create. V means verbose, so it'll show more information, and F is for file. So F, after F, you put the name of the file that you want to operate on. So that's, and if you're interested in, and I can't remember if I talk about this later, but I mentioned it before. There's a utility called man, which stands for manual. If you put man and then the name of one of these commands, it'll give you documentation of these. I mean, it's pretty lengthy. It's more for reference, but you can see here that it'll define each of these arguments or options that you can pass to the tool. Yeah.
How did you search this manual?
So this is, I think I had this in the slides. I went over this very quickly. The man page is, I think, the same tool as less. So we talked about less. Less is a utility that allows you to kind of interactively browse the text of a file. And it has commands that are similar to Vim, which if you pick Vim, or you go over the tutorial for it, you'll learn the commands for it. You can use the arrow keys and page up and page down. The way to search through it is with /. All these commands are very, very esoteric. You kind of just need muscle memory to relearn these over and over. But if you do / and then type a string to match and hit enter, less or the man page will highlight those matches, and you can use N to she, all the matches, Shift N to go backwards and search. So these are all super they're very lengthy sets of command line instructions for these, and you can learn these over time. I would pick a couple of simple tasks like let me just search, and then let me try that a few times, and then when you forget it like I do the next 10 times, you just Google it again and just say, all right, how do I use search? And then eventually you gradually remember the small number of commands you need to do what you want to do. And that's how I learned it. I basically just Google it when I forget how to do something. And then I do that 10 or 20 times, and eventually I remember it for a couple months, and then I forget again. And, yeah. Okay, so let's go over this homework real quick. Let's do a couple examples of these. So here's the original tree. I improved the instructions a little bit, based on some feedback. I made this so you wouldn't get, so if you got lost in your directory tree, all of these commands would still work. But they're minor changes. But this is what, if you look at the homework tree, when you unzip it, I haven't actually untarred it yet. If we look at the tree, this is what it looks like originally, and this is the new tree that I did some file operations in order to get this modified version of the tree. I don't know if anyone tried this, but you could just recreate this whole tree from scratch. That's actually one solution. Did anybody try that? Did anybody just do okay, so one clever person decided to. So that's not the minimal number of instructions, right? But that is one way to do it. You just create the whole tree. That's like you just delete, you remove everything. Yeah, I didn't show the remove. It's a little dangerous to remove entire trees, so I didn't show you to do it. But the rm command can be used to recursively delete a subdirectory. So if you try to delete a directory that's not empty, the remove command will not let you. Same with remove dir, won't let you remove a non-empty directory. But you can force it to do it. And you can look that up on your own with man rm. But yeah, you could, if you've ever seen online the people who troll unfamiliar users, will say, type this sequence of commands, and it deletes your entire file tree. That mean thing to do. That's the command I'm talking about. You can easily recursively delete all of your files. So be careful with rm. I think there's an interactive mode to make sure that you don't. Maybe that's move. There's an interactive mode to make sure you don't delete stuff without prompting. So you could use it safely like that, -i. Anyway, so yeah, that's the outside the box way of doing it. It's funny that somebody actually thought to do that. That's good. But the sort of minimal way is to make small changes to this tree so that it matches the new tree. So let's take a couple examples. We went over ext2 in class. Let's look at net Ethernet. So what's the difference between net Ethernet in the previous tree and in the new tree? Yeah.
That doesn't have any subdirectories.
Doesn't have any subdirectories. There's no files in it. Yeah.
Ethernet has changed the sound.
Okay, so one solution is to move Ethernet to sound. So I gave no constraints on what files were the same or not the same, or whether they're even directories or files. So you could certainly avoid recreating sound by moving another file. What are other ways to make net match net here? Yeah. Delete Ethernet. Yeah, you can delete Ethernet. It doesn't have to be combined with, but you could, to make a smaller number of operations. But yeah, that's what we can do to make the net subtree match the new net subtree. So what command? So here I'm in the homework 3 directory. What commands would I enter in order to make that happen? Let's try deleting the Ethernet. Yeah. So we could use rm-r. Let's avoid using rm-r. Let's do it without. Let's just do rm. Yeah. Yeah. Go ahead. Oh no. So, yeah.
What's rm-r?
So rm-r recursively deletes. So if you have an entire subtree of files, like, well, all right, let me just show it working. So rm-r will take this entire tree, this entire homework 3 tree, and normally when you just type rm, it'll say, I'm not going to remove a directory. Rm is meant by itself is removing files. If I say remove recursively, what the manual says is that it removes directories and their contents recursively. So it'll just blow away, or at least remove from the directory entries, every directory starting from the path that you give it. So if I do like rm-f root, what's it purportedly going to do? Delete everything. Now, you don't have permissions to delete root, and I would very much annoy the sysadmins if I somehow had permissions to do that and did that. That would be very bad. But so I can't delete this tree now. But let me, let's just delete the whole tree. So rm-r, recursive delete the homework 3 folder. And since I can't remove the directory without removing all its entries, it will recursively enter. And actually, I didn't have time to get to this, but I wanted to ask you guys for an algorithm from deleting an entire tree. And it's really just a tree traversal. You just traverse, it's like a post-order tree traversal. You just traverse the tree to the leaves, delete the leaf, then delete the parent, because the parent is now a leaf. Once you delete all of the leaves, the parent of the leaves are now leaves. And just recursively traverse that tree, deleting all of the files and directories in a bottom-up fashion. I mean, I haven't looked at the algorithm, but I'm pretty sure that's what it does. Yeah?
If using the dash or when that cross-space O of n operations, is the streams not sorted?
Yeah, it would take O of n for the number of files. That's right, the traversal.
How does it so quickly then on certain streams not?
I think it's just removals really quickly, or I mean, I don't know what the operating system does under the hood. I don't know if it actually goes in and it bothers to delete all these files. I think it does, because otherwise these files will still exist. Yeah, I don't know. I'm pretty sure it does recursively do it. I think it's just very fast to do removals because it's not deleting the data. It's just deleting all of the entries, the directory entries. It doesn't actually delete the file's data. If you remember when we talked about how files are implemented very briefly, these are just, the file name is just an entry that points to a directory entry that points to the data. And so when you delete a file, you're just deleting that entry, not the data. You're effectively deleting the pointer to the data and not the entry itself, basically. Yeah, no problem. So I suspect that's why it's so fast. I haven't looked at the remove command source. We could. It's open source. But I suspect it is doing this recursive traversal. So now if I try to look at the homework 3 tree, it's gone. Everything is gone. So this is why using rm-r is a little dangerous, especially when combining it with wildcards like star. I don't even want to type it because I might just blow away all my stuff. But yeah, that's what rm-r does. Questions? Any other questions on that? So that's one way we could have done it. I'm going to restore this tree here. What's another way without using slightly dangerous commands to get rid of Ethernet? Yeah.
Remove directory.
Okay, remove directory. And remove directory what? If we type remove directory Ethernet, well, there is no directory Ethernet. That's because we're in the homework 3 folder. The homework 3 folder contains net, but the Ethernet file is under the net subdirectory. So, as your colleague just pointed out, we would have to remove net/Ethernet. And what kind of path is this? Relative path. And relative to what?
Net.
Relative to net? What's that again?
Homework 3.
Homework 3. It's homework 3. Our working directory, print working directory, is homework 3. So this path, so Ethernet is relative to net, but this path, net/Ethernet, is relative to the current working directory, which is homework 3. Other questions on this operation? Yeah.
Would you alternatively enter net and then just delete
Absolutely. So let me do it this way first and show you the new tree. So now net no longer has Ethernet. I'll restore this tree. So I untarred the file again, so Ethernet is back. So you could certainly, instead of using a relative path to go to a different directory, delete a file in a different directory, you could just change the working directory to that subdirectory net. And now I'm in homework3/net. The only child here is Ethernet, and I could just remove Ethernet from this new working directory. Could certainly do that. So change directory in my opinion, makes things a little more confusing because you have to keep track of like where you are. I like using paths because I can stay in one spot and not disorient myself on the file system. Other questions on this? All right, so maybe a deceptively simple exercise. You have to kind of do a little puzzle solving, figure out the right operation, keep track of your working directory. And just remember, always type pwd ls so you don't get lost in your file system. You kind of have to have a mental model of where you are on the tree when you're working in the command line. And pwd and ls will keep you up to date so you don't have to make any assumptions about where you are. All right, so that's navigating the file system. Hopefully those of you who haven't seen the command line are a little bit more comfortable, I hope, with using the command line. And when we go into the projects, I'll give you, at least in the beginning projects, very specific instructions for moving around the file system. And then hopefully over a couple months, you'll be much more comfortable with the command line. You can kind of make your own workflows and work however you prefer. There's no real one way to navigate the file system. There's many ways to achieve the same goal. And so once you get comfortable, I hope you'll get comfortable in a couple months. So when you do the later projects, you'll have no issue using the command line. All right, other questions on navigating the file system? All right, so that was the file abstraction. So we learned briefly the kind of theory behind the file abstraction. What is a file in this Unix world, the file abstraction? What is a file? Data, so that's what backs it. But abstractions are really defined by what you can do with them, how you can operate on them. So how is a lock defined? A lock is defined because you can lock and unlock it. Doesn't matter how it's implemented. It might be metal, it might be steel, it might be wood. You can have a wood lock. But it's really the operation. So what operations unify files? Yeah.
A way to store information.
How do you store information with a file?
Basically,
You write bytes to it. You read and write to. If you read and write bytes to something, you could model that with a file in the Unix world. So I'm sure I think you've all done C programming where you have to like open a file, right? Like fopen, read and write. So that read and write, those read and write operations, these are system calls that the kernel provides you to read and write files. But the file itself does not have to be backed by, it doesn't even have to be backed by some physical data. It could be something in memory. It could be a socket. It could be a thermometer that you hook up to your machine. And in the Unix world, you could treat that as a file and read and, well, not write to a thermometer, but you could read from the thermometer, read bytes from it. And using this exact same interface that you use for reading and writing files on disk, you can read and write really any kind of hardware you like, as long as you can implement what reading and writing means for that. So a thermometer might be continuously sending temperature data, and you could open it as a file, call the read operation, and every time you get the read operation, it gives you like 2 bytes of a temperature or something like that. So that's the file abstraction. That's why it's an abstraction, because it's an interface that's independent of how it's actually implemented behind the scenes. And if you've taken object-oriented programming or will take it, you'll see that this notion of abstraction kind of pervades programming. With object-oriented programming, it's one way to define new abstractions for yourself in a programming language. But in the kernel world, the abstractions are defined by the kernel, by the operating system, and then it exposes a library of commands, an API for operating on its abstractions. Okay, so that's the file abstraction that we learned about, and most of the time you're going to be dealing with files on disk and file hierarchies. But good to understand that abstraction is the operations you can do on some object, and the file abstraction is just you can read and write on data. So today we're going to learn about another fundamental operating system abstraction called a process. So has anyone learned about processes before? A little bit. What did you learn about it?
Basically, you learn how the cache. Basically, you learn basic transferring, like memory, cache, and so on, and CA. Kind of covered. Sorry.
No, that's okay. So you learned some implementation details of processes, like how you can make memory accesses faster for processes, and probably virtualization. Did they talk about virtualized memory, perhaps?
Not really, not architecture.
So you might learn about that in operating systems, and you'll learn more about that. I'm going to give you kind of just the broad strokes of processes. But a process is sort of deceptively, just like files, a very deceptively simple definition of what a process is in the operating system world. A process is just a running program. I mean, who cares? I mean, you have a program, it can run. Why do you need some fancy abstraction for this? So first of all, what is a program? You guys have all written programs. What is it? How can you define what a program is? Yeah.
Blocks of code that do something you need it to do.
Sure, code, like machine code. So you might have, for instance, actually, I think I have a diagram I can show for this. Oops. So this is a really good, free, and open operating system textbook that you might use if you take an operating system class. And it defines it the same way. A process is just a running program. So it's easy to say that, but it's a little more subtle when you look at the hardware point of view. So typically when we have a program, we persist it to disk. When you save the hello world, then you compile it. Now you've got a hello world program. That machine code, you store it as a sequence of bytes on disk. And at that point, it's not running. The machine is not running. It's just stored on disk. And to have something running on the machine, it means the processor is executing its instructions. So it's a subtle distinction, but there's the program itself, which is just a sequence of instructions. And then there's a running program. There's a machine that's actually executing sequences of instructions. And in order for that to happen, which I probably learned a little bit in computer organization, in order for the machine to start executing a stored program machine, the code somehow has to get into memory, and then the CPU has to go to the first instruction of that program and start executing it. And because of the whole fetch execute loop that modern processors have, the CPU will automatically fetch its next instruction and go through each line, not necessarily in order sequentially, but go through each sequence of instructions in that program as you've coded it to do. Does that make sense? Questions on that? It's almost too basic to even say, but when we think of a process is not the program on disk or some sequence of instructions, but it's the program that is currently executing on the machine. And so at any one time, there are lots and lots of programs on your machine because they're stored on disk, but not all of them will be running at the same time. And depending on your machine, you may only have one program running at any one time. For most people's machines, that's more or less the case. You probably have one processor. Okay, so that's a process. Why does it matter? Why do we need to make such a big deal about a process? And why do we even need an operating system to manage this for us? Why can't we just write a program, write some code that loads it into memory and just run the program? So on your machine, for instance, why do you need to care about a special product? Why don't you just run a program? You just run a program in your machine, right? Yeah.
Because we have multiple tasks.
Right, exactly. You have multiple programs that you probably want to run, at least for our modern day computing devices. We have lots and lots of programs that we want to run at the same time, but most of us have one processor. Maybe it has 8 cores, but you're probably running more than eight programs at one time. Yeah. Right. So, I mean, the point is, what if the process crashes? Well, if you're just running run program on your machine, your whole machine just like stops. So that is actually another function of having this process abstraction and having the operating system manage it, is that if there are failures in the program, then the operating system there is to recover for you, to terminate the program, give you the dreaded seg fault. But your machine still runs, hopefully, even if one of your programs enters some failing state. So yeah, one of the main problems with computing devices that operating systems help overcome is that you have many programs that you might want to run at the same time. And there are lots and lots of ways to solve this problem. We're going to look at one way today, but how can we solve this? Let's say you have one machine, one processor, and you want to run 10 programs. How can you run those 10 programs? Yeah. You could have them take turns. Okay, you could have them take. So who's gonna do the turn taking? Are you gonna sit there and stop the machine and load a new one? Okay, so you could have some program that helps them take turns. What else could you do? Yeah. You can have more CPUs, but let's say I give you n+1 programs, where n's the number of processors. What are you gonna do when you have not enough CPUs for programs? Yeah.
Right, prioritize the order all the programs are executed based on what the user is actually.
Okay, so you can ask the user to order them somehow. And then what were you going to say? Scheduling, but how do you schedule them? I mean, so who does this? Who does this work of scheduling them? So who does it? I mean, yeah, go ahead. Well, the operating system does. You write a program to do it. Sure, yeah. So one simple way that I didn't hear, which is kind of funny, is you could just like run them one at a time. I didn't say it once. I just said you have like 10 programs to run in one CPU. Sorry, that was maybe that was a gotcha question, but you could just run them one at a time. It's called batch processing. It's what lots of machines did. Yeah. You switch really rapidly. Yeah. So that I think we have a couple of people already sort of foreshadowing what modern operating systems do. Yeah. You can use what? Multi-threading. I mean, these are all the same, actually relatively the same solution. So the way I'm going to talk about and what Unix and other modern what are called time-sharing systems do is they make the CPU or they make the programs take turns, and so that you have the feeling of programs running at the same time, they make them take turns really, really fast. So you can imagine you have 10 programs to run and you let each one take, an hour and then switch. And for high performance machines, like high performance computing machines where they have, processes that take hours and hours and hours, this may be one strategy where they do batch processing or they have very long time deltas for switching. On our modern mobile devices and desktops, they're using Unix and other systems of the time pioneered of time sharing, where they not only switch between applications, they switch between them really, really fast, to the point where for at least some of the time, you have the illusion that the programs are running simultaneously. Now, I'm sure you've had programs hang where it's not making progress, and you've not had this feeling that they're running at the same time, and that's partially because that program is really slow or not responsive. But time sharing is a technique where you have many, many programs you want to run, and what the operating system does, as many of you pointed out, is they make the programs take turns on the CPU, and they do it so fast, like many, many times a second, or once every few milliseconds or 500 milliseconds, switch between these applications. And because modern PCs are so fast, you get this illusion of simultaneous execution. You can also have multiple CPUs, as one of your colleagues pointed out, where you can actually have multiple programs executing at the same time, but those are finite. Yeah.
Does that mean that technically the programs are running slower?
Yes, yeah, it does mean the programs are running slower. I mean, so strictly speaking, yeah, they will, in some cases, always have to run slower because they're sharing time with the CPU. And in fact, they may even run slower than if you would run them back to back because of the extra time taking to switch between them, because it takes extra computation time to switch between processes, which I'll show you why that is briefly. But yes, it will it can make all the programs run slower. Now, not necessarily. There are a bunch of tricks that if you take OS or an architecture class, you'll learn about, where if one program is waiting for input or waiting to write to disk or write to the screen, that time is wasted anyway. They're not using the CPU. And so the operating system can schedule a different process to run during that natural pause in the program. So for certain workloads, you can minimize the amount of slowness that every process gets. But if you're doing long-running computation, yeah, there's not much you can do to make that even as fast as running programs back to back. Okay, so time sharing is the technique where you give you slice up the time that each program has to run on the CPU. And the trick, the abstraction part of this, so there's many ways you could do this. You could write programs that are aware of the operating system and actually tell the operating system, hey, I'm done for a little while, schedule someone else. But the way time sharing works is it uses the process abstraction. And the process abstraction gives each program the illusion that it actually has exclusive access to the memory and the CPU. So let me try to diagram this briefly. So this is our physical hardware. This is the CPU and the RAM. And as I kind of hinted at in the first class, the kernel is the lowest layer of software that mediates your program's access to the hardware. And it excuse me. And it provides this kind of idealized or virtualized view of the hardware. So when you write programs, you don't have access to actually touch directly hardware. The operating system mediates that access to the hardware for you. And so with the process, what it does is it in a sense copies for each running process on the that you've executed. So you have only one. If you only have one processor, there's two here. But if you only have one processor on your machine, then each running program is given a virtual bubble where the program believes that it is exclusively running on the processor and that it has exclusive access to the entire RAM space, to your entire RAM. And so this is where the process abstraction becomes a lot more meaningful at the operating system level, because for the running program, you as the programmer can write hello world without worrying about all the other programs that are running on your machine. You can just pretend that you're going to be loaded into memory, an exclusive access to memory, that you're going to get exclusive access to the processor, and your entire program will be run. And so the process abstraction defines what the process has access to and how it gets mediated with hardware. And it's the operating system down here at the kernel layer that looks at these two running processes and schedules them to actually run on the machine. Yeah.
Is this similar to how virtual machines work?
This is very similar to how virtual machines work. Yeah, you can think of a kernel as a virtualization layer. Now, virtual machines historically were emulators, where instead of giving access to the physical hardware, so modern operating system processes, your program will be running on physical hardware. Like your instructions will be loaded into the CPU. With traditional virtualization or emulation, like emulating game consoles, for instance, the hardware you're running the virtualizer on is not necessarily the same as the hardware you're virtualizing. So maybe you're emulating an NES, a Nintendo from decades ago, but you're emulating it on an x86 architecture. So in that case, the software, there's a software definition of the machine that is executing, pretending to be the hardware executing the operations. But in this case, and actually modern virtualization as well, have techniques for making sure that the programs actually run on the bare metal. So it is very, very related, virtualization. And in fact, modern operating systems have support to make virtualization faster so that they work much closer to this, where the virtualized programs are just getting time to run on the bare metal. So yeah, very related. You can think of the kernel as providing hardware virtualization in a sense, but it does it in a way that's much more efficient than just straight up emulation, software emulation. Okay, other questions about this? So each one of these bubbles is a process. And we'll actually see some commands for how we create processes and look at processes on the operating system. But at its most fundamental level, the kernel provides an API for you to create a new process and to replace that process's memory with whatever program you want. There are actually two commands, fork and exec, which we'll look at in a couple of weeks. And so, yeah, the kernel provides this API for creating and managing processes on your machine. And the beauty of a process is that it makes each program believe that it's running exclusively on the hardware. And without having to know anything else as the programmer, the operating system will schedule use of the actual hardware for each running process. So because of this, we can have hundreds, thousands of running processes on a machine that has a single CPU, and you as the programmer don't have to do anything special to take advantage of that. All you have to do is know how to call the kernel and tell it to create new processes for you. Questions on this? Questions on the process abstraction? So what's a process? A running program. That's all it is. And the reason that we have this abstraction is for scheduling and providing this illusion, this virtualization of the hardware. Okay, so to see a little bit about how this actually happens at the hardware level, let me show you the same. So this book has like a homemade kernel to illustrate some of the ideas, and the way processes, the way the kernel manages swapping between different processes is actually pretty straightforward. The CPU, if you remember computer organization and logic, how much state does the CPU have? So we have RAM, but we have the CPU. The CPU has some state, has some information that it holds on to. What are those called? Registers. It has registers. And that's really where almost the entirety of its state lives. Now there's complexity with caches and RAM, but fundamentally the processor's state is just in its registers. And so what the operating system does is every time, so actually the way schedulers work is every X number of milliseconds, the kernel will take over, start running, and when the kernel takes over, that stops whatever process is running, and it literally copies the values of the registers at that time. So the process, your program stops running, the operating system copies all of the state of the CPU, stores it in memory somewhere, and then restores the state from a different process or starts a new process. And then it starts running. That process stops. The operating system takes over, records the state of that CPU, puts it into memory, and then restores your old process that was frozen. And it just does this over and over and over, many, many, many times a second, freezing and restoring the state of your process. And that's really all it needs to do in order to resume what your program is doing at the CPU level. Does that kind of make sense? Yeah.
Let's do this like similar to thread. Multiple threads going on at the same time.
So threads. There are several ways to implement threads, but you can certainly use processes. There's something called kernel threads, which are effectively processes that work the exact same way. Yeah. So you can implement threads using kernel processes. They sometimes call them lightweight processes because you're managing them within the same program, so you don't need all the same information for a different process. But effectively here, these are the same idea as threads. It's how you can implement concurrency on the same hardware. Excuse me. And then there's other information that processes have associated with them, like open files, where they have RAM. So the RAM is divided up in a different way. It's virtualization, which you'll learn about if you take operating systems. And when we talk about processes and standard I/O, there are also files associated with each running process. But in order to achieve this time-sharing trick, all you really need to do is copy, save, and restore the CPU state. And the CPU won't know any difference. except for, say, caching, which actually can lead to security vulnerabilities. But in this theoretical model of a CPU, all of its state is in its registers. All right, questions on processes and how this magic of processes work? Yeah.
Yeah, so you have like a bunch of separate programs running in various processes. Would you run into an issue where you're just getting like really high cache miss rates because it's loading everything into the cache and maybe overflowing
Yeah, 100%. So what your fellow colleague is asking is, if you're swapping all the time, and so you probably learned from computer organization that the CPU is caching RAM accesses and instruction and data accesses, and so can the cache go stale every time you swap it? Absolutely. Yeah. So there are. So this is outside my expertise, but there are designs that will help ameliorate this. There's algorithms for when you evict stuff from the cache. There's a separate cache for virtualization that helps keep the translation faster. There's all sorts of tricks at the architecture level and at the OS level to make sure that you have like better cache performance. And people actually like spend a lot of time optimizing kernels, hardware designs to make sure that when you're running a browser and your email that you'll run as fast as possible, that you'll avoid slow RAM accesses. So sure, yeah, there are lots of techniques for doing this in computer science. Outside my expertise, I don't research these. But yes, that is a problem, caching. You can also just have a larger cache. It's one solution to deal with it. All right, so that's the process abstraction. Let's take a look at how, in the Unix world, we create new processes. So there's where's my slides? So there are two instructions that are used to create processes in the Unix world. The first one is called fork, and perhaps counterintuitively, fork doesn't actually create a new running program. It just copies your process in its entirety, including the program. So when you run fork, you actually have two copies of the exact same running program, which seems a little counterintuitive. You want to run a new program. So there's another instruction called exec, which overwrites your running program with a new running program, with a new program machine code. And so you can run these separately. You could run exec by itself. You could write a program like Hello World that then executes ls. And you can just call exec and say, okay, operating system, after this point, after exec, I want you to take this other machine code from disk and I want you to overwrite my memory and start executing that code. That's what exec does. So it doesn't actually create a new process. Fork will create a new process. And in the Unix world, these are decomposed into two separate steps. Yeah.
So fork will save it though, so you need to do it again.
So yeah, fork will, the two programs will continue running when you have fork. And the common idiom is that in one of the new programs you call exec to replace it. So that way your old program's still running and then your new program is also running in a new process. So we'll actually write this when we actually got to implement our own toy shell, and we'll actually use fork and exec to run programs the way bash does. So kind of like I put up the cell division here, it's kind of like cell division where you make a copy of an existing process. And interestingly, this is actually the only way in user space to create a new process in the kernel world. But that kind of begs the question, how do you create the first process? And so when you boot your machine, the first process is created during the boot process, outside of your control. It's called init. It used to be called init. I think nowadays systemd is managing the init on a lot of distributions like Ubuntu. But basically, during the boot process, one of the things that happens during boot is the very first, root process is created, and then any new processes that are created during the lifetime of your running machine are all forks of init or some child of init. So what you end up with is a process tree. So you can see trees show up a lot in computing. You have this init process, and when there's a lot of programs that get created during boot after init. But new programs are created by forking from init, and eventually bash will be forked when you log in. And when you start running your own programs, like, for instance, you run pwd, bash will fork itself. It will go fork itself to create a new process for you and execute the pwd program. And then when pwd is done, it will the input of your keyboard will return to bash so that bash can fork other commands like ls. And so you end up with this process tree, which you can actually see on your own system with, there's a couple different commands for running it, but ps is the program for inspecting running processes. And this little secret sauce here, axjf, will print the kernel tree. So here's the init process. It's actually a program called init. You can see it has process ID 0. It is the very initial process. And then all these there's a little ASCII art here to show you child nodes here. But all the other processes are some descendant from the init process. We can even look for my own, oh, sorry, that was loud. I can look for my own my own processes here. So here's my SSH session, where the SSH process, so SSH is another program, it's a process, and it's a child of something, probably of some SSH daemon. It forked an SSH version of SSH for me. This ultimately forked bash, and you can even see here is the PS program forked from bash and less, because I also ran less to view the output of this. So here's the process tree in the real in your Unix machine. Questions on this? Questions on the process tree, the style? And you'll read about this tonight. So if your homework tonight is reading about like this design, yeah.
Are there some question marks?
Yeah, that's a good question. Where's the question mark? Oh, here?
Oh, yeah.
Oh, this is the what do they call it? Teletype? What they used to be called? This is like the terminal. What terminal it's associated to, or what terminal it's writing out to. So most of these processes are not associated with a terminal. So the ones that are like logins from people. So you can see we can actually spy on the other users on the system. So other people are logged into the system and they have different terminals. So in the old days, there were physical terminals that were connected by wire to a machine. Now we have virtual terminals like over the internet. Yeah.
Is this homework for?
No, this is not homework. Homework will be reading about processes. Yeah.
So that was showing all of uses, not just your system.
Right. All of Eustace. Yeah, this is all of Eustace. You're going to at least look at the processes for all of Eustace, so we can actually see. Okay. Yeah. Let's not look at that. But you can see mine at least. Yeah. So if I had other running processes here, as you'll see in the video that I recorded for next time, the advanced processes, Eustace does not allow you to keep processes running when you exit, which is a little unfortunate because there was a tool I'll show you next time in video that benefits from being able to be run after you exit, but Eustace is configured to not permit that. So all these people are logged in, have maintaining a connection to the machine. Okay, so there's processes. There's the Unix philosophy of how processes are created. They're always created by forking an existing one. So that means you have to have an initial process. That's the init program, which you can actually see here. Actually, you can see threads here as well. So I don't really know how this is implemented, but I suspect this is the kernel functionality for doing pthreads, like kernel threads. This is the init program. So there's literally a program, I guess, called init. That is the first. So it's systemd. It's systemd nowadays on Ubuntu. So this is the init program. Okay, questions on the kind of theory of processes in the operating system world? Yeah.
So does all processes on Unix run from the initial init?
They don't necessarily run from it, but they may run from a descendant of it. So that SSH daemon actually might be run from init, but my bash shell is run from the SSHD process, which itself has init as an ancestor. So just like in this tree here, where my bash shell, its parent is like SSH, the SSH daemon. And yeah, so all the ancestors, the ultimate ancestor of all processes is init on the machine. Okay, so let's look at how we can actually work with processes in bash. So one of the benefits of using a shell is that we can have some pretty low-level control over the operating system, including processes. Yeah.
Sorry, it's probably a dumb question, but what's the bash?
Oh, sorry. Bash is our command line shell. So bash is the name of a program that implements a command line shell. So the command line, it's another program. Actually, it's another process that runs. And there are other shells like Z shell or TC shell. There are other implementations of command line shells. They're command line processing programs. We'll write a simple version of a command line processor for one of our projects. But bash is the name of one of the implementations of a command line shell. And it has its own syntax and its own scripting language. And yeah, it's a popular one. It's the one I use, yeah.
Yeah, so on that note, so is the shell like just the terminal, or is it just the layer of conditions that we have?
The shell is the program that you interact with. The shell is just a program that you interact with, that you type commands into. I think it's called a shell. I think it's called a shell because it's a very lightweight program that allows you to operate over the kernel. I don't exactly know the history of it. Yeah. What's that? Oh, because it surrounds the kernel. Well, the kernel itself has protections, hardware protections against it.
Yeah, but it's how the user interfaces with the kernel. Like,
Okay, yeah, I think that makes sense. So the shell wraps around the kernel. It's like a thin wrapper around the kernel that allows you to access a lot of the low-level features of the kernel, like what I'll show you today, like process management. Yeah, so that's all bash is. Yeah, not a bad question. Bash is the name of a program that is one implementation of a kernel, an operating system shell. Okay, so let's go over using the shell to manage processes in the Unix world. So I already kind of previewed some of these. If you want to view all the processes that you've created in your bash session, you can think of these as the descendants of your bash session, more or less. The PS command, which is kind of short for processes, will show you those processes. If you want to view the processes on the whole system, you can use PS AUX. And so I'll show this trick next time, but you can use the less command in order to navigate through this whole list because it's a giant file. So you can scroll backwards too if your terminal allows it. But here's all the running processes on this is Eustace. So these are all the processes running on Eustace. And I don't think this is secret information. Everyone has access to this if they can log in. Yeah. A bash session is, so when you log in to, so the reason that, let me go back to my login here. So when you call SSH on your machine, you're opening an internet connection to Eustace. And when Eustace receives that connection, after it does authentication, it starts running a program on your behalf. It runs the bash program. And what the bash program does is it just reads your text that you type over the SSH connection, over the internet connection. And so all that really happens, all SSH really does is it just, when you connect, it just starts running a program for you. That program happens to sit and wait for your input. And it waits over this virtual terminal. And when you type ASCII, when you type on your keyboard, ASCII data goes to that bash program. And that bash program interprets that instruction and then does whatever it's programmed to do, whatever you ask it to do. Does that kind of make sense?
So then what's the difference with bash, with viewing all the processes in bash?
So the only difference is whether they're basically programs that you invoked during your bash session versus programs that were invoked by others on the machine. So it's just by default, the PS command will only print the processes that you've invoked from your current bash session. Think of it as like the descendants of your bash session, whereas PSAUX will just will give you all processes in the entire machine. That's all it is. It's just a convention. It's like when you type CD without arguments, there's some default behavior. And the default behavior of PS is just to show the processes that you've invoked in this current SSH session. We already looked at the process tree, AXJF. This will show the whole tree. Okay, so running programs, creating new processes in Bash, we actually already saw this. It's very straightforward. You just type the name of a program. Bash will go out, find the program, and it will fork an exec for you. So that's why when we saw the tree here, you saw that PS, which I invoked from the command line, is a child of Bash. So the Bash program itself ran fork and exec and started and created that process for you on your behalf. And the command line shell, this design, it's designed by people, but the way they designed it was you just literally type the name of the program and it will go off and create the process for you, the running program. So that's all you need to do to run a program. You just type the name of some existing program and hit enter, and it'll go create that process for you. So we talked a little about command line arguments. This is just also the design of the shell. This information will be passed to the running program. So if you've ever written int main or int main, int arg, argv and argc, you wrote that, right? You probably wondered why. Why do I have to do that? The convention is that the information from the shell command line, all this stuff after the command, gets passed to your main method through argv. That's where that information goes. And it's just a convention in the Unix world to use that information in order to control the behavior of your command line program. Yeah?
Is there a reason why it gets passed as an array, not just a single element?
I mean, I think it's just design. The Bash, it's kind of an interplay between the design of the shell and the design of Unix programs. So the shell will break up the arguments for you ahead of time and pass a list of those arguments. It could certainly just pass you a big string, right, and just make the program do it itself. But it's just a design to pass in arguments. And you can see these conventions here. There's a function called getopt, which helps with command line processing in the kind of Unix style. Okay, so how does the shell know where to get these programs? So ls is obviously not here in my current directory. So in the kind of Unix world, there's a list of directories that the shell looks at in order to look for programs. And again, this is just a convention that is used in the Unix world. If you want Bash to tell you where it found that program, you can type the which command. So which will give you the full absolute path of the program that it matches, that it finds from this set of paths. So that's why, and this is exactly why if you compiled a C program yourself and you were hoping to run it with hello, the Bash is going to be like, no, I don't know where that program is. The reason is because your current path, this PWD path, is not known to Bash as a place where programs live. But you can always give Bash a path, a relative or absolute path to a program, and run it that way. So that's why you have to type / in the Unix world. It's just a design. So that programs that are run without a path are given in a well-defined set of directories. And there's some kind of sensible security reasons for that, I guess. But that's just the Unix design. Okay, so that's the path. So I went over this already. So there are some commands. So I type which cd. There's no path here. Why is that? Because actually cd is a built-in command in the Bash program. So Bash will interpret your commands. There are some things that are built in, like cd, and so they don't have a program for them. Okay, so let's say I write a program named cd. How would I run that program? Yeah. /cd, yeah, or whatever path to it is. Exactly right. That's how you do it. So cd is a built-in that Bash reads, and it won't let you run a program called cd. Yeah, but you can always give the path to it. Yeah.
What are echo, $, paths? What is path?
So path is an environment variable. Another design of the shell is that there's a set of persistent variables that bash maintains. And these range from a lot of things. You can see here, it's like the name of the shell program, the language you're using, your current working directory. And one of those is the path, and the path defines the set of programs that bash will look up. It's really just part of the bash design, that these notion of environment variables. And actually, all Unix shells have this.
So it just holds all like the normal bash commands.
No, it just holds data. It's just data that is used by various tools, used by the shell environment. So for instance, there's no like one use for these environment variables. It's just a data store, persistent data store for the shell that you can use for all sorts of things. One thing that it uses it for is to store the set of paths to programs, the set of paths to system programs. And these are all like configurable. Okay, so let me get through standard I/O in the Unix world. So another Unix convention, in addition to shell variables and the design of the shell, is that every process in the Unix world is given 3 files every time a process is created. So this is done by the system. So there's some kind of enforced file I/O, file standards that are on every process that gets executed. And these 3 files are standard in, standard out, and standard error. And so collectively, these are called standard I/O, which is kind of tangentially related to the standard IO.h in C. So the question is, why do this? Why make every process have 3 files? Why don't just let the programmer open it? So what do you think? Like, why bother doing this? Why force every program to have a, yeah?
If the programmer themselves doesn't do it, or something happens to it when they try to open it in assessment, sorry, when it just like they close it by accident, they could cause an error, I guess. Am I?
Sure, yeah. If you leave it up to the programmer, then they may not do it. They may not. Oh, yeah.
It allows us to use multiple programs and chain the programs together and type the output.
Okay, so somebody who knows the Unix world already. I'll show this next time where you can. So one of the benefits of this is you exploit this to link together or chain together multiple executions of programs, piping their input and outputs together. This is a more advanced thing that I'm going to show next time. But I think part of this is also that it comes from this focus on the interactive shell. So whenever I invoke a program, the shell is always, or the terminal is always there as input and output. And so if the shell is always there as input and output, and like your fellow student said, if the developer didn't bother dealing with standard I/O, then where would the input and output from the shell go? You'd have to like tell each programmer to do that. Instead, the operating system provides standard I/O, and the C library with like printf. So when you all wrote printf, you didn't bother saying where it should go. You just said just printf. And the reason that works is because the operating system gives you a standard output on every process. And printf, you don't have to open a file. You don't have to, like you said, you don't have to remember where to put it or where to write that information. Yeah.
Is that why that when you include studio.h?
You include studio.h to standard.h. It's actually standard. It's standard I/O is what it stands for. Yeah, it does look like a misspelling of studio. But that includes the library functions for operating on I/O. It's more than just standard I/O, but it also operates on I/O, file I/O within C. But yeah, so I think a lot of the reason is that by having a default input and output, if you have an interactive shell, then you always have a place for information to be passed into the program and information to come out of the program. So when you're running the shell, standard I/O, so echo is another program. So echo is a program that just takes whatever argument you put on the command line and prints it out to standard out. So where does it go when you're running in an interactive shell? It just goes to the terminal session. The terminal session can read data and can write data. But where does standard in come from? So cat is a program that writes out whatever its input is. Whatever input you give it, it'll write it out. And so again, without saying anything else, the bash session already has input and output from the terminal. And so it'll just redirect that input and output to whatever running program you've executed. So cat will take whatever input you give it and write it out. So I can write hello world here, and you can see it gets printed out by the cat command. Yeah.
So there's a cat, that's why cat is different from touch, right?
Yeah, touch creates the file on disk, but cat will read from in the standard input, which when I'm running bash is my terminal, and it'll write to the standard out, which when I'm running bash is also my terminal. Yeah. Yeah.
So the standard input is the bash itself, or is it whatever we're putting as argument?
That's a good question. So standard input and output is not defined ahead of time. It's so you can change so in other words, in the program, the programmer doesn't have to know where standard in and standard out comes from. That's kind of the beauty of it, is that the operating system just gives you standard input and standard output. Depending on how you execute the program, you can change where standard in and standard out come from. So when you're running bash, the bash program will make your terminal session standard in and standard out.
So we'll take inputs from the terminal session.
Exactly, yeah. Yeah, so when I run cat here, so grep is a command that searches for a string. So if I write a bunch of text into the grep command, and one of my lines is hello, you can see that the grep command will write to its output whatever input matches that it matches the argument that I gave it. Okay, so this seems almost a little like trivial, like why, I have a terminal, I write to a program and I read from it. The beauty of standard in and standard out is that because it's not programmer defined, it's operating system defined, you can, from outside the program, change and redirect where standard input and standard out go. So I give this example with grep. So this is one of the cool tricks with the bash command line, is that I can write some extra suffixes to my commands to redirect standard output to different places. In this case, I can redirect to a file. So here, normally when I type ls, it writes to my shell, because standard out is now being redirected to my terminal. But I can redirect it to a new file. So this is my ls out file. And you can see the terminal no longer shows the output. Instead, the output has been written to a new file. So here's the new file here, ls out. And the cat program, if you remember from last time, cat will print out a file to standard out. There's the text of the ls command. Does that make sense? Sort of. So whatever output a command has, I can add this little arrow suffix and a name of a file, and it'll create a new file, and instead of printing the output of that program to the bash terminal, it will create that file and add that text to the file.
So when the out file, the where it's not there, the where it's not out file, just create the file and without like the text.
It creates a new file. This file called new file. Let me give it a better name. So ls output. It creates a new file called ls output. Oops. You can see here I have a new file called ls output, just created just now, 1316. And the contents of this file, like if I type less or whatever command you want to use to print it out, the contents of the file is the output of ls. So it took whatever program you ran, whatever output it generated to standard out, like the programmer ls probably wrote printf, whatever output it had, or my hello world program, for instance, writes is just printf hello world, I can redirect that output to a file. And that's without changing anything in my hello world program. So when you wrote hello world, so this is hello world, it just said printf. Printf prints the standard out. And because you're printing to standard out, my shell can change where that output goes. So in this case, I redirected it to a file called out file for hello. And here's the text of that file. Yeah?
What if the file I kind of write to, like, the state, would it overwrite it?
It's going to overwrite it, yeah. So you have to be a little careful when you use it. So I could overwrite my out file for hello here. And now my out file for hello has been overwritten with the output of ls. Yeah?
Can you append it?
Yes, you actually can append. I didn't show that here, but in the slides. But if you do a double arrow, that's a very good question. Very, very, very good thinking. If you have two arrows, then it will append So I'll just append a whole bunch of times to my out file. And you can see here, there's the old text from ls and hello world multiple times from running that multiple times. All right, so we can also redirect the input as well. So let me do an example with grep. So normally if I look at this user include standard IO file, it's going to print out this big long header file. And remember, grep will take your input, and whenever it finds a line that matches, it will write it to standard out. So if I grep for include, but redirect its input, so I'm not typing it on the command line, instead I redirect its input from a file using an arrow the different direction, then what do you think I'm going to get as the output? I think I've lost people.
Yeah.
So when I run grep include by itself, I have to type in stuff to pass to grep. And grep will match whatever lines I type in. So it matched include. If I instead pass in a file, yeah.
It would print out all the includes in the file.
Yeah, exactly. It'll print out all the lines that match the word include. So instead of me having to type things to pass to grep, I tell the bash shell to take this file, pass it as the input to grep, and then grep will run as it normally runs. And this is all without having to change the grep program. So just because grep works with standard in and standard out, like printf and scanf, it will just take whatever input is given to it by the user, or by the person who created the process. Yeah.
It's kind of like how in CS1 we would run our programming center with a shell and then be able to compare it with what we're supposed to get really easily.
Actually, yeah, you probably redirected to a file and then ran diff or something. Yeah, so exactly right. So that's why it helps with development. Yeah.
Can you redirect the standard in and the standard out?
Yes, you can do both. So I could redirect and say to a new file and save a new file called all include, and now the results of grep will be in that all include file. Exactly right. Okay, so it is, okay, so class is over at this point. I think I've basically, so I've covered everything.